Hello, my name is Ever Barbero, and today I'd like to talk about stress concentration. This is a lecture for MA 343 Intermediate Mechanics. We're in Chapter 5, which is failure, and today we're going to talk about stress concentration. So, in the mechanical material calculation of stress for mechanical components, we calculate the stress in bars simply as P over A. For that, the bar has to be longer than the cross-section, at least 5 times longer than the cross-section. For beams, we use for one plane bending, that will be minus y m over I to calculate the stress. And again, the cross-section has to be smaller than the length of the beam. Okay, a ratio of 5 at least. And for shaft, we have the shear stress, which is the torque times the radius divided by the polar moment of area. And again, the cross-section has to be smaller than the length. In addition to that, it is assumed that the cross-section has no holes, notch, fillets, threads, grooves, tool marks, etc. There is no discontinuity, no change in cross-section, no abrupt changes for those formulas to work. All these things, holes, notches, and so on, are called sometimes notches in general, but better call them stress racers, because if they're present, they increase the stress above what is calculated with mechanics of materials. All right, since calculation of mechanical material is very easy and we can do that fast and accurately and confidently, we would like to see if we can calculate the stress caused by these notches also in a simple and efficient practical way. Okay, so here we have two things. We have a shaft of diameter, large diameter is capital D and small diameter lowercase d, and the change in diameter is accommodated by a transition with a fillet that provides a smooth transition between one and the other, and there is a radius for this fillet, and that is important in the magnification of the stress. And okay, so in this side we have a rectangular bar, the thickness T, side height D, and we put load P axial, and there is a hole of lowercase d diameter. All right, so if we concentrate on the shaft, we see that we can define two stresses: the nominal stress, which will be the stress if this reduction of cross-section did not happen. That means if the shaft was capital D in diameter. So the area will be pi diameter squared over 4, and the stress is just P over A. All right, so that's mechanics of material stress. All right, but then there is another stress, which is the net stress, we call it, one that we calculate with a smaller area. In this case, the smaller area is diameter D, so pi D squared divided by 4. And we calculate again another stress, and this stress is higher because D is smaller. So this net stress is higher than the nominal, but not high enough, because in this region there will be a stress concentration that will be above the number calculated in this region. The stress is calculated with mechanics of material like these and these are the stresses that are okay far from the discontinuity. These are the discontinuity or the stress racer. So let's say over here, yeah, it's okay. But for this part, no, it's not okay, because the perturbation caused by this region, it will extend to here and it will affect the calculation over here. Okay, so since calculations using mechanical material are simple, we want to figure out a way to extend this to calculation when we have practical mechanical components like these with holes and with changing cross-section and things like that. All right, so then to explain this, what I did is I did the finite element analysis of this bar. It has thickness T. You cannot see the thickness, because the way the FE program works, it doesn't show you the thickness. But I don't want to use FEA analysis because it's too complicated for preliminary design, and I don't have time to explain it. So that will be another course later in the senior year. But I do this because that way I can show you what a good approximation of the reality. And we can compare the calculation we can do easy with this calculation that it took me a while to do, even though I I have a lot of experience working with this FEA business. All right, so what I do is I have this bar with some thickness T, which is 1 millimeter, and the width is 10, and it has a hole of diameter 5, and the length I put 60. So it's not too long, it's barely long enough to allow this region to develop the stress calculated with strength of material. So based on the diameter and the width, the D over W is 0.5, we're going to need that later. And then I have to put material properties, which you don't need for statically determinate structures with the mechanics of material methods. But with FEA, you have to have material properties. So I had to put steel, 207 GPa, Poisson 0.29, and the yield strength I put infinity. Really, you cannot put infinity, you put a big number. I put a big number, so no matter what load I put, the material will be elastic, and so then you can see the stress concentration. And then I can talk about what happens when the material has a finite value of S of Y. Then I put a load, and then of course for this case, the nominal stress will be P over the area here, and the net stress will be P over the area when we take out the hole. So W minus D is what is left. That's what is called net, because that's what the cross-section is reduced to that. I only keep this. This is gone because I drill a hole through it. So 10 minus 5 times the thickness 1 is 5 millimeters squared. That's the area. And then when I do sigma P over A, 1000 over 5, 200. So 200 MPa, okay? So the stress in this region, the stress in this region with the mechanics of material should be 200, but it's more because there is the hole, and the hole is a stress raiser, and you'll see it's more. Here I will try to explain a little bit how to set up a model using a finite element analysis software. Just a little bit, you have to take other class to understand this, but just a little bit so that you understand that there is some complexity involved and it's not so trivial, okay? So in the previous picture, we've seen a bar with a hole, and now when I try to do the calculation to calculate the stress, that's what I want to do. You see that I put only half of the bar. And so why I put half of the bar? Because this is usual in finite element analysis. We try to include in the model little as possible so that the computation of the stress doesn't take a long time. In this case, I pick half of the bar because I know this problem is symmetry with respect to this line. That means the geometry is the same on both sides, the load is the same on both sides, the boundary conditions are the same on both sides. So how this is done is that you impose symmetry boundary condition with a feature that the software has, and it's easy enough. You just select this line here and this line here, and you click and you say symmetry with respect to this plane, and then it's done. Okay, that's easy. I could have a model only a quarter by applying also symmetry along this line, and okay, but I decided to do the easy way to make it easy to explain. So I model 1/2. So then I have to put the load. Now, if you go put the load at one point, which in FEA, finite element analysis, in FEA will be called a node, then what you're going to get is you're going to get a stress concentration here, which is not real because you're never going to apply the load like that to a real structure, just at one point. And so the load somehow is going to be applied in practice, distributed, will be distributed over this region to make it more or less uniform, all right? And so this can be done in two ways. One is a dirty way, which is to transform the load into a pressure, but you have to be careful with the units of the pressure, and I don't like it because I'm not applying a pressure, I want to apply a load, right? So the elegant way is to use constraint equations. That way I put the load there, and then I say to the software that all these nodes have to move together with this constraint equation. And then I'm going to get a nice uniform stress here, which is going to be correspond to the one that I calculate with the nominal area. So load divided by nominal area will give me the stress in this region over here. And over here in this region, I'm going to get load divided by net area, and I'm going to get that. And then these points over here, I'm going to get the maximum stress, and from which I can calculate the stress concentration factor. And one last thing that sometimes you have to do is to put a rigid body motion constraint, because the model without this model cannot move horizontal, but it can move vertical. Okay, the orange triangles indicate the direction in which it cannot move. So it cannot move horizontal, but it can move vertical. Forget the blue triangles; those are for rotations. And so that means that when I pull here, sure, it's not going to move horizontally, but it could move vertically. But you say, well, it's not going to move vertically because the load is zero. Well, in the computer, nothing is truly zero, because there is, you know, 0 could be 10 to the minus 32, but if there is no constraint, then it might move, all right? And so the best is to constrain the rigid body motion by putting this little triangle vertical so that this point doesn't move up and down. Some software do this automatically. Actually, the software I use for this does this automatically, but I put it on purpose so that you know that sometimes this is what you have to do. Okay, usually what happens is you set up the model and the results are garbage and you don't understand why. And one thing that I always say is go check if there is rigid body motion. Okay, for that you plot the deflected shape and you'll realize. Okay, so with that, I have set up the model and then I run it and I calculate the stresses, all right? So what we do is we go here. And so now here we have the bar deformed and with the stresses. The first thing you notice is how come you say you're going to calculate on half, but now you have the whole bar. Well, this is a trick, because since the solution is symmetric, and there is a feature that you can just select this and say plot symmetrically and it will fake this one. So this is a mirror copy of the ones on the right. It's put on the left, yes, for your enjoyment, yes, to make it pretty. Okay, so now the deformation is exaggerated. In practice, this is steel, a real material. You're never going to see things deforming like this, like bubble gum. But the software automatically or under your command can magnify things so that you get an idea what's going on. And so you see the deformation. The magnification is so huge that the circle became an ellipse. So okay, so then let's see what value do we get. All right, so over here we have a color-coded von Mises stress. I could have plotted sigma x, but I picked von Mises. It's the same. For this particular case, sigma x and von Mises are the same. So, okay, so here we have colors and which represent the values of stress. Now, this is not very accurate because, you know, there is a range. You could go from 1.3 to 37. And what color is the dark blue? 1.3 or 37? No, any of these values falls into blue, all right? So there is a little bit of an error you can incur if you trust too much this scale, okay? But at the maximum, yes, I trust, because red cannot go more than 434. And red is here, so that means that the maximum stress is 434. All right, but is this value true? Okay, let's check, all right? So this is something I always do with finite element analysis. I check if the solution makes sense. And I know that this stress over here is very easy to calculate because we are far from the hole. So the stress can be calculated with mechanics of material formulas, P or A. And what A? The A nominal I will have to use, right? So P divided by A nominal gives me, let's say, 1000, P divided by A nominal, which was 10. So that's 100, right? So blue is 100. And is that true? Yes, because this is the blue. And then it goes between 73, yes, there is a 1 here, to 109. So, but believe me, it's 100. It's not 73 and it's not 109. This is because of the artifact of the contour plot. But because mechanics of material tells me it is 100, I trust. It's 100. So let's see the net. Oh, the net is the load divided by the area net. The area net is 5, so that will be 200. So the net will be in this region. Okay, let's see this green. Yes, the green goes from 181 to 217, and mechanics of material says 200. So I get the net stress, I get the nominal stress, the deformation looks right, then I trust this stress is 434. Now I realize how huge this is, because the net is 200, and it's magnified more than twice to 434. So it goes really high. The stress concentration is really high. It's 2 point something, yes? 2.2. So how come? Well, this happens because the material was modeled as elastic. For this amount of load, 1000, the material didn't yield, the solution is elastic, so this magnification of stress happens. And if the material is brittle, which means it's never going to yield, then the stress concentration factor will have to be applied because this magnification will always happen. But ductile materials are nicer because ductile materials you see in the next video that they yield and they soften the peak of the stress, and they soften it a lot. All right, so you will like to see the next video. Okay, so here we go. All right, so now with FEA we can calculate the maximum stress, but it's a little bit of a hassle to set up all this stuff. So what we can do is we use the graphical method. All right, graphical method means that we have charts of theoretical T, the T is for theoretical, stress concentration factor KT. All right, then what we do is we calculate the net stress and we'll multiply by KT right here. So why the net stress? Because the chart, the caption on the chart says use the net stress. You have to read the caption all the time for every chart. And if it says use the net stress, then go for it, all right? If it says the nominal, you use the nominal. So you multiply here the stress, in this case net, times the theoretical stress concentration factor, and you get the maximum sigma x. Now the chart does not provide a stress concentration factor for von Mises, but in this case, von Mises and sigma x are the same. And so how do you read the KT? Well, this is a no-brainer. D over W is 0.5 because of the dimensions D and W. So I enter with 0.5, then I go there to the left, and I'm a little bit below 2.2, so I'm going to pick 219. And then multiply 219 by 200, that's 438. Versus FEA, 434. I mean, this is so good, it's uncanny. You think I'm cheating, but no, I did this in different days. This FEA I did quite a while. And this calculation I did today, 438 versus 434, and this calculation for me was like 5 minutes, okay, versus hours to get to the FEA model running. Okay, so that's it. I mean, this is the way we're going to do. For every problem, you find a chart that applies to that problem. How? You look at the pictures, this picture. This picture is going to have two things. First, geometry, so it's going to be like a bar with a hole, or a bar with a fillet, or a bar with two holes, whatever. Then the other thing is going to vary is the loading. So you're going to have axial loading like this, bending, and torsion, 3 loading. So there are, for every geometry, there are 3 charts, and you have to pick the correct one. Then see what stress, how do they want you to calculate the stress? Usually it's the net. Then you go with these parameters and go there, read, get this number, multiply the stress, boom, you got it. Okay? All right, so conclusion, but the video is not done. I just want to put the conclusion here, so then it will be more emphasized. So if the material remains elastic, I'm saying this in anticipation of the next video, okay? If the material remains elastic, no plasticity, the stress peaks near notches. It does, you've seen it. So in a way, I did the FEA because it's more believable because you see the picture, okay? So the stress concentration can be calculated with charts, no brainer. Now be careful to use the correct stress, nominal or net, as indicated by the caption on each chart. All right, let's solidify this with some examples. So I'm going to have example 1 and 2, which really are part of one example, which is this geometry, right? So this geometry has 2 notches or stress racers. It has a hole, which we know is going to kick the stress here at the edge of the hole a lot. And also it has this fillet with a radius 1 millimeter, which is small. So that means when you have a changing cross-section, like from 40 to 34, you don't want a sharp corner there, because a sharp corner, if it is absolutely sharp, is going to shoot the stress to infinity. Believe me, when we see fracture mechanics, you're going to believe me. So what people do is put a fillet. Anyway, if you machine this, you cannot put 0 radius, because there is no tool on earth that has 0 radius as a tip, no matter how sharp it is. And so, but you put a decent R. And the thing is, you'll see that the larger this R, the better you are, because the stress concentration will go down. For this example, we put 1. And then we load it with 10 kilonewton, that's 10,000, all right? So, okay, first on example 1, let's calculate the stress concentration factor and the stress, I guess, at the hole, all right? The hole is 4 millimeter diameter, this is 40, yes? And so we calculate left of the fillet, nominal is 40 times 2, this 40 times 2. 80, and then we calculate the nominal stress, which is 10 kilonewton divided by 80, 125, okay? Now what about the net? Net is how much area do I have if I drill the hole? Well, 40 minus 4, because diameter is 4. And then multiply by 2, that is the thickness, you got 72. And my net stress, 10,000 divided by 72, that's almost 139. All right, so it grew a little bit, but you see the net doesn't grow so much. It doesn't grow enough. Now, on right of the fillet, this will be, for example, 2 really. The net area is a smaller area, which is on this side. So basically it's easy, 34 times 2, and that gives a stress of 147. Okay, so that's to differentiate between nominal and net. We got that. And so then this chart you've seen already. And it's just that now we have to enter here, as you see in the next picture. Yes, the figure caption says use A net, which is W minus D multiplied by T. All right. And okay, so then we go here, and so around the hole we have A net, which is 72. We've done that. Sigma 0 is this. We've done that. And so how do we read the chart? Well, for D4, W40, which we know, right? D4, W is 40. D over W is 0.1. So then we go back here, and we enter through 0.1, and we go up there, and we read here, 2.6, 2.8, in the middle is 2.7. And okay, so 2.7. And it says use the net, so 2.7 times 138.9, I get 375, okay? So you see 2.7 is large, right? You notice, for example, that for a bar with a hole, when D over W is 0 or goes to 0, because D cannot be 0, otherwise you have no hole. But if it's super small, then the hole thinks that it's in an infinite plate, right? If this D is very, very small, this width looks very big to the hole. So if it's in an infinite plate, the value is 3. For holes, the maximum value of KT is 3. There is an analytical solution and proof for that. And it's nice to remember, because if you don't have the chart and you're in a rush, well, the KT for a hole cannot be more than 3. So you can use 3 and it's conservative. Later, when you get your hands in the chart, then you can correct, and then you realize for this geometry it's 2.7. All right, so then we have that, and it's 375. All right, we gotta remember that, it's in red. So then we say example 2, that is basically the same example. Now we want to calculate the stress concentration factor at the fillet. The fillet is there, right? And so we have a different chart, right? And now this chart has more parameters. We need R over D. R is the radius of the notch. Always R is the radius of the notch. So it could be the R of a hole, the R of a fillet, various things. Divided by D, careful here, this D is the small d, not the large D. That's the way they did the chart, okay? Not my choice, okay? So now the solution is given parametrically for big D over D, small d, because it's a fillet and it makes a difference how much you jump from this big D to this little d, yes? And so you gotta pick this curve, all right, one of these curves, by calculating this. And then, of course, you read the KT over here, which has no dimension, so great, no dimension. No, we don't have to worry about units. And the figure caption says use A net, which in this case is D times T, because the net is this and times the thickness, all right, the smaller of the two areas. All right, so then, okay, here's the picture again. Now we are on the right of the fillet. The A net is 34 times 2, that's 68. Sigma net is 147, okay? So now we have 34 and the fillet is 1, so R over D is 134, which is about 0.03. And d over d is d over d, okay, is 40. D is 40 divided by 34, that's 118. Yes. Now, if I go to the previous slide, you'll see there is no r over d is 0.03. How come? Well, 0.03, yeah, there is. I could, right? Yes, I could do that. 0.03, yes. Okay, I didn't think about that. All right. Anyway, when I did the problem, I take r over d 0.025. All right. Actually, when I did the problem, I was doing the charts from the book, which are not as good as my charts, and that's why I couldn't see 0.03. All right. And so I don't see d over d 1.18, and so I take a 1.10. Yeah, this remains true. 1 point whatever is not there, so I take 1.10, which is the gray line. Yes. 118 is not there, so I pick 110. Couldn't I pick 120? No, it jumps to 150. Yes. So no, 118 is closer to this, so I pick the gray. Okay. So I take that, and then I go here, and of course with my 0.025 I go there, and I get this number, which is 2. Okay, so from caption, use net stress, calculate this, which is 147, is right here, multiply by my number, which is 2.2, and it's 323. Okay. Okay, so that means that the maximum stress at the root of the notch, which is going to be right here, right there, is going to be 323.4 or something like that, close to that. But from the previous case, for the hole, I got 375. So forget this number because the hole, in this case, controls. The critical point is around the hole. So if I ask you, calculate where the bar is going to fail, well, you have to say here, because the stress is 375, not 323, provided the material is brittle, as we will explain in the next video. All right, so re-emphasize the conclusions. If the material remains elastic, the stress shoots near the notches. The stress concentration can be calculated easily from charts, and we are going to use the correct stress, nominal or net, as indicated by the chart, by the caption in each chart. Okay. So next lecture is notch blunting. You'll see how why the ductile metals are the king of manufacturing. Why everything, almost everything, is done with ductile metal. You will understand in next video. Okay, in your car, everything is ductile. Nothing is brittle. Most machines, ductile. Airplanes, ductile. Civil infrastructure, ductile. You look for ductility. You will understand in next video. All right. So the videos are here or here later on YouTube. Homework, everybody knows the homework where it is. All right, so with that, thank you very much. Okay, I'll see you soon.